This is the continuation of address translation of virtual memory. So the address that is generated by the processor is called the virtual address. The virtual address contains the virtual piece number and an offset. So in a piece, it contains a number of bytes, and the offset specifies the byte within the piece. So which byte within the piece, that is decided by the offset. We have a base table base register. The base table base register contains the starting address of the base table. So the starting address, the address from where the base table begins, is indicated by the base table base address. It holds the address of the base table. So the starting address will be placed in the base table base register. And the entry in a base table is calculated with the help of base table base register. The content of base table base register content is added with the virtual page number. We will get the entry of the page in the page table. So the page table holds the information about each page. This includes the starting address of the page and in the main memory. So here we have a page frame. Page frame is nothing but the place to hold the page. So normally photo frame. If it's a photo frame means what? It holds the photo. So the page frame means the place to hold a page is called the page frame. So the page table contains the page frame and the control bits and some control bits. So when a processor needs some when we converts the virtual address to physical address, the virtual page number is added with the page table base register. Then we will get the particular page table entry. So we will get the page table entry. From the page table entry, we will take the page frame. So the page frame and offset will give the physical address in the main memory. Page table entry for a page also includes some control bits which describe the status of the page while it is in the main memory. One bit indicates the validity of the page. So that indicates whether the page is actually loaded into the main memory. So allow the operating system to invalidate the page without actually removing it. So when the page table page is available in the main memory or not, it is decided by the validity of the bit. If the page is valid, that means the information in the page is valid. The value is indicated by the validity bit. If the page is still in the page table without removing it, if the content of the page is not correct, then the operating system can invalidate it by using this validity bit. Another one bit that indicates whether the page has been modified during its residency in the main memory. The main memory main memory place what is the content of the secondary storage copy and main memory place the copy of the content that is placed in secondary memory is placed in the main memory also. But if the content is modified during its residency in the main memory, നമ്മുടെ മെയിൻ മെമ്മറിയിൽ ഇരിക്കുമ്പോൾ അതിന്റെ കണ്ടന്റ് മോഡിഫൈ ചെയ്തിട്ടുണ്ടെങ്കിൽ അതിനെ ഡിറ്റർമൈൻ ചെയ്യാനായിട്ട് നമുക്കൊരു ബിറ്റ് ഉണ്ട്. സോ ദിസ് ബിറ്റ് ഡിറ്റർമൈൻസ് വെദർ ദ പേജ് ഷുഡ് ബി റിട്ടൺ ബാക്ക് ടു ദ ഡിസ്ക് വെൻ ഇറ്റ് ഈസ് റിമൂവ്ഡ് ഫ്രം ദ മെയിൻ മെമ്മറി. ദാറ്റ് ഈസ് സിമിലർ ടു ദ ഡർട്ടി ഓർ മോഡിഫൈഡ് ബിറ്റ് ഇൻ ദ കേസ് ഓഫ് ക്യാഷ് മെമ്മറി. ഈ ക്യാഷ് മെമ്മറിയിലും അങ്ങനെ ഒരു ബിറ്റിന്റെ കൺസെപ്റ്റ് നമ്മൾ പറഞ്ഞായിരുന്നു. അതായത് നമ്മൾ ദ കോപ്പി ഓഫ് ദ ഡാറ്റ ഇൻ ദ സെക്കൻഡറി മെമ്മറി ഈസ് പ്ലേസ്ഡ് ഇൻ ദ മെയിൻ മെമ്മറി. സോ വെൻ ഇറ്റ് ഈസ് ഇൻ ദ മെയിൻ മെമ്മറി, ഇഫ് വി മോഡിഫൈ ദ data in the that particular page when it is residing in the main memory. So while replace when the memory is full, we need to replace the content. So while replacing, we need to write it back to the disk or secondary storage. നമുക്ക് രണ്ടും the same data ആണ് വേണ്ടത്. നമ്മൾ ഇവിടുന്ന് പേജിനെ റിമൂവ് ചെയ്യുമ്പോൾ നമ്മൾ this particular bit, control bit will indicate whether the data is modified or not. Data modified ആണെന്നുണ്ടെങ്കിൽ നമ്മൾ write back in, remove in the time. Where should the page table be located? So we recall that the page table is used by memory management unit for every read and write access to the memory. So ideal location of the page table is within the MMU. Then ideally MMU nathanu varundhathu. But page table means it contains the information of all the pages. All pages in information avada varum. അതുകൊണ്ട് ഈ MMU എന്ന് പറയുന്ന യൂണിറ്റ്, this MMU unit is a part of the processor chip. So to include this larger page table in MMU is not possible. So the page table will be kept in the main memory. So the page table is not kept in the main memory, memory management unit, but it is placed in the main memory. A copy or a small portion of the page table can be accommodated within the MMU. So the portion consists of page table entry that corresponds to the most recently accessed pages will be placed in the MMU. Not all pages, but a portion that is frequently accessed will be or most recently accessed will be placed in the MMU, and rest of the page table entries will be placed in the main memory. A small cache called transition look-aside buffer is included in the memory management unit. So transition look-aside buffer holds the page table entries of the most recently accessed pages. നമ്മൾ cache memory case പറഞ്ഞു, that is the processor instead of accessing the main memory for all the data, the frequently accessed data or the recently accessed data will be placed in the cache memory. And the same concept ആണ് നമുക്ക് ഇവിടെ വരുന്നത്, that the page table is placed in the main memory, but a small cache of the page table is placed in the memory management unit. Memory management unit വരുന്ന processor chip നകത്തായിരിക്കും, so that the processor can easily access the memory management unit. So അത് ആ cache എന്ന് പറയുന്ന പേരാണ് transition look-aside buffer. Recall that cache memory holds most recently accessed blocks from the main memory. The operation of transition look-aside buffer and the page table in the main memory is similar to the operation of cache and the main memory. Cache memory, main memory പോലെ തന്നെയാണ്. നമ്മുടെ TLB അത് MMU അത് വെക്കും, and page table is placed in the main memory. So ഈ page tableന്റെ തന്നെ ഒരു cache ആണ് നമ്മൾ transition look-aside by TLB എന്ന് പറയുന്നത്. The page table entry for a page includes address of the page frame where the page resides in the main memory and some control bits. നമ്മളിപ്പോൾ page table entries നമ്മളിവിടെ കണ്ടു. Here we had the page table contains the address of the page in the main memory and some control bits. In addition to the above, for each page, transition look-aside must hold a virtual page number for each page. So here this is the transition look-aside buffer. Transition look-aside buffer ലാതെ നമുക്ക് virtual page number കൂടെ ഉണ്ട്. ഇത് കൂടാതെ virtual page number കൂടെ നമ്മൾ transition look-aside buffer place ചെയ്യും. So the page table contains page frame and control bits, but in transition look-aside buffer we include the page number also, virtual page number also. So associative mapped TLB, transition look-aside buffer, that is higher order bits of the word. So higher order bits of virtual address generated by the processor selects the virtual page number. So we already discussed that virtual address from the processor, it contains a virtual page number. So this higher order bits generated by the processor select the virtual page. These bits are compared to the virtual page number in the TLB. You can see here that the virtual address generated by the processor, it contains virtual page number and offset. So this virtual page number here, it compares with the virtual page number in the TLBs. So if there is a match, a hit occurs and the corresponding address frame is read. So the corresponding address plane will be red. And if there is no match, a miss occurs and the page table within the main memory must be consulted. So set associative maps TLB is found in commercial processors. Here it is associative map. We already discussed when we studied about the cache memory what is associative mapping, what is direct mapping, and what is set associative mapping. So associative mapping means we can map to any location in the cache. So here TLB is the cache of page table. So from the page table entry can be placed in any part of the TLB. How to keep the entries of TLB coherent with the content and the page content of the page table in the main memory. Coherent means the content of the TLB and the content of the page table in the main memory should be the same. So the operating system sometimes changes the page table entry of the page table in the main memory. So simultaneously it must also invalidate the corresponding entry in the transition look-aside buffer. So a control bit is provided in the transition look-aside buffer to invalidate this entry. If an entry is invalidated, then the TLB gets the information for that entry from the page table. This is the same case that happens when a miss occurs or if the entry is not found in the TLB. The same process happens here also. What happens if a program generates an access to a page that is not in the main memory? So this case is called a page fault. A page fault is said to occur. So when a page fault occurs, the page that should be executed at that time should be brought from the secondary storage to the main memory. We currently execute in the program data that should be placed in the main memory itself. So page fault occurs when it is not in the main memory. Processor request in the data instruction program the main memory page fault. So at that time the data or the instruction will be taken from the secondary storage and should be placed in the main memory. So upon detecting a page fault, the memory management unit follow the actions. That is, it will ask the memory management unit will ask the operating system to intervene by raising an exception. So the processing of the active task which causes the page fault is interrupted and the control is transferred to the operating system. The operating system copies the requested page from the secondary storage to the main memory. Once the page is copied, the control is returned to the task which was interrupted. And servicing a page fault, it requires transferring the requested page from the secondary storage to the main memory. So this transfer may incur a long delay. So while a page is being transferred, the operating system may suspend the execution of the task that causes the page fault, begin execution of another task whose pages are available in the main memory. So this enables efficient use of the processor. So how to ensure that the interrupted task can continue correctly when it resumes execution? So there are two possibilities. The execution of the interrupted task must continue from the point where it was interrupted. The instruction must be restarted. Which specific option is followed depends on the design of the processor. When a page is to be brought into the main memory from the secondary storage, when the main memory is full, some pages from the main memory must be replaced with this new page. So since the size of the main memory is relatively larger compared to cache, a relatively large amount of programs and data can be held in the main memory. Minimizing the frequency of transfers between the secondary storage and the main memory. So when the transfer of data accessing the secondary storage, it will take more time. So while increasing the size of the main memory, we can minimize the frequency of transferring data between the secondary storage and the main memory.